Hi, everyone. Cuong Do's come up from YouTube this afternoon to tell us a little about how they grew that organization very quickly as its popularity skyrocketed over the first couple of years in its existence. With very few people, they built an amazingly scalable system. And I think that it'd be fun to hear how.
Great. OK, so again, my name is Cuong Do. I was part of the original engineering team that grew YouTube from its infancy to its current scale. So here's what we'll talk about. I'll go over a little bit of the history, basically, where we've been, how long it took us to get here, and I'll go into the evolution of the scalability of the various parts of the system, the main parts of the system. So I think over the course of today, you've probably seen this kind of graph a number of times. So in the context of this presentation, I guess it could mean a couple of things. Well, Google has great free food, so yeah, jeans are getting a little tight here. I hope it's the Google stock price in 2007. Or what it actually is, though, is the daily video views per day of YouTube.com since its beginning. And its beginning was a little more than 2 years ago. So here's a quick timeline just to give you guys a sort of frame of reference. We were founded in February 2005. We got our funding kind of in October 2005. And there's only a couple numbers I can really share with you due to various reasons. But in March 2006, we actually hit our 30 million videos served per day milestone. And in July 2006, just 4 months later, we more than tripled that. We were serving an average of 100 million videos per day. So you can kind of extrapolate some of the numbers. I mean, we've definitely grown very rapidly since then, and we continue to grow very rapidly. And obviously, in November 2006, we were acquired by Google. So to give you some idea of how small the team really was, we basically had 2 sysadmins, more or less, 2 software architects dealing with scalability issues. We had 2 feature developers doing everything that the users see. We had 2 network engineers building a network that was pushed tens of gigabits per second, and 1 DBA, and we hadn't been bought by Google, so no chefs yet. So here's a kind of quick little algorithm that I came up with to handle rapid growth. So you identify and fix bottlenecks. You drink, you celebrate, you sleep, and you continue the process all over again. And that really has been our general motto. I mean, we have tended to go in these very, very quick cycles, and sometimes we go in these cycles, we do all these steps within the span of a day, and sometimes less than a day, so we don't get much sleep sometimes. And if you think I'm kidding about the drinking or sleeping parts, and no. So yeah. So OK, the first area that I'm going to talk about is our web servers. So here's sort of the basic setup. I'm kind of omitting details about how many machines and such, because I want to just explain the overall flow of requests. So first, the requests hit the NetScalers, which are load balancers. They're actually really good load balancers that do a number of things. They mark down machines and mark up machines, and they cache some static content for us, which is good, because Apache is not very good at handling large volumes of requests for static content. And they do a couple other things like connection pooling to Apache. The request then hits one of many web servers that are sitting behind these NetScalers. And these web servers are running Apache on the front end, because Apache is fairly well tested. It has a huge community. We know how it works. And Apache is running modfast CGI, which basically looks for requests that look dynamic, that follow certain rules that we defined, and shoves those requests to the Python app server that we've created. And that does most of the work. That does the application-specific work for us. And I'll go into a little bit more detail about what that means. And the app server then talks to various databases. It calls information from various sources, gathers all that information, and spits back an HTML page which then gets served to the client through Apache. So general flow. So a few more details here. The web servers run Linux, They run specifically SUSE Linux. And the nice thing about the web servers is that you can generally scale just by adding more machines. It's not always the case, but more often than not, it has been the case. One thing that we've seen from various blogs and even from people who we brought in to interview and were potential candidates for software engineers, we always ask the question, why Python? Is it fast enough? And one interesting thing to note about web applications is that CPU is often not your bottleneck, at least not CPU on the web servers. It turns out that you're often spending time waiting on a number of things. You're spending time waiting on the database. You're spending time waiting on your various kinds of caches. You're spending time waiting on a lot of RPC calls. I mean, granted, web CPU is important, but it's not the overriding concern for web applications. So that's one thing. Another thing is because we're in a particularly fast-moving field, we have, it seems like dozens of competitors announced every single week. And we have scalability concerns, so we need to be able to move around pieces of code very quickly. We need to be able to rewrite things. Development speed is often actually one of the most critical things. So that's where Python excels. So I guess the answer to the question, is Python fast enough? Well, I guess the key word is enough. It's definitely fast enough, and we can add more machines and add capacity that way. So on our web servers, we tend to aim for much less than 100 millisecond per page rendering times. So basically, as soon as the app server gets the request and parses it and then generates the HTML and gives it back to the web server, a lot less than 100 milliseconds in general, which is fairly important because you don't want all your processes getting too busy on your web server. We use a couple of things to speed up Python. We use Psycho, which is basically a just-in-time compiler for Python, which will compile certain pieces of code, namely the ones that matter most, the tightest loops that we do, into C. So another thing is we also selectively wrote certain things, such as some of the encryption stuff, as C extensions. Another way to sort of take advantage of Python as well as use some of the speed of C. And the last thing one of the other things that we do on the web servers is we pre-generate HTML. So in some cases, you can do various forms of caching. You can, on the lowest level, you can cache rows from the database. On the slightly higher level, you can cache fully formed Python objects, which can be serialized to disk fairly easily. And at the next level, you can actually cache full HTML, which is often a pretty expensive operation, like to generate that HTML. So in certain cases, when there are blocks of HTML that are fairly expensive to compute and to render, we just cache all the HTML. So the next area is serving video. And the costs are fairly predictable in a lot of cases. Bandwidth is certainly an issue. The cost of hardware is certainly an issue. And power consumption. We have a limited amount of power that we can get in any one particular data center. So we need to be judicious in that. We need to pick hardware that doesn't consume an excess amount of power. So in the YouTube system, each video is hosted by a mini cluster. A mini cluster is just some small number of machines that serve the exact same set of videos. And they have various forms of redundancy. And the reason why we have a couple of machines in each cluster is that, one, scalability. You have more disks serving each content. You have headroom. So if a machine goes down, the other ones can take off the slack. And it's just nice to have basically kind of like online backups of everything, more or less. So it serves multiple purposes. So originally for video, we started with Apache. And Apache was fine for 3 months, maybe 4 months. Didn't work very well. It had such high load. It had very high context switching because of all the processes or threads that were active at any given time. So we switched to lighttpd. Well, lighttpd is an open source web server, and it's a lot faster. It uses single process, single thread, and some very efficient things like ePull, which allow you to basically pull a large number of file descriptors very efficiently. And we switched from single process to multi-process. So again, it's just an iteration of the same idea. So for video serving, we have a couple of different paths that a video request can take. We actually put the most popular content into the CDN. And we have a couple of different CDNs. We use some third-party CDNs, and we also have internal Google-produced ones. And we have a couple other things that we're kind of playing around with to see which one is the most effective one. So that's for the most popular content. And the moderately played and the lesser played content actually go to the regular YouTube servers. And what's kind of interesting about this is that because the most popular content has gone to the CDN, the traffic profile of the requests that go to our regular machines is very interesting, because some of these videos might have between 1 and 10 or 20 views per day. In the scheme of things, not very much. But when you add up the whole thing, when you aggregate that, and when you look at the percentage of our overall playbacks that constitutes, that's a huge deal. And the problem is that when you have a large amount of data and you have kind of random access across that data, that introduces some interesting performance characteristics. You suddenly emphasize random disk seeks, so suddenly your RAID controller becomes more important, your caching becomes more important, and you want to tune the amount of memory on each system so that it's not too small, so that your cache is not thrashing all the time. But it's not too large, because otherwise, when you expand the number of machines, it's just costing you too much money, and you're not gaining that much benefit. And there are some other things we also were able to tune, like some controller settings and stuff like that. But the point remains, like, our machines have to be tuned very differently from the CDN machines, which are mostly serving out of memory. So here are some key points. We keep things simple and cheap for the most part. We make sure that not too many network devices are in the path between the client and our video servers. We use commodity hardware, which is important because we found that the more expensive hardware gets, the more expensive everything gets. The more expensive the support contracts get, the less likely you are to find a random Usenet posting or random forum posting about that hardware. So we try to keep generally within the kind of the mainstream for servers. And we use simple and common tools, rsync, SSH, and a number of other things that are just bundled with Linux for the most part. And we build layers on top of those because those are well tested, and if we need to, we can actually modify them. So in case you guys were wondering if all the fun that we've had is over after Google acquired us, here's a recent email that was sent out. Certainly woke me up. We had 3 days left of video storage, and we need to scramble and stuff like that because apparently we had a spike in uploads. We had a number of things that were going on. So we got that resolved, but it's just amazing the kinds of things that you run into when you're dealing with a site that grows rapidly and grows very unexpectedly. Because the moment we relieve a bottleneck, the site traffic goes up and a new bottleneck appears. I mean, it's that simple. Even if in some cases, we double the number of machines, and site traffic still picked up within a couple weeks. So thumbnails is the next area I want to talk about. And surprisingly, thumbnails is actually a pretty difficult problem, at least when you use most of the conventional methods. Because thumbnails, the thumbnail images that correspond to each video, which I think are 120 by 90 pixel images, they're small. They're around 5K each. And the thing about thumbnails is that there are a lot of them, because each video has multiple thumbnails. So so I think each video has about 4 thumbnails. So suddenly there are 4 times more thumbnails than there are videos. So that becomes an interesting problem, especially since the videos are spread across a whole bunch of machines. They're spread across hundreds or thousands or whatever machines, whereas thumbnails are concentrated on a small number of machines for various reasons. And so you have the overhead of dealing with a lot of small objects. You have INO caches. You have directory entry caches. You have page caches. You have all these different caches that get involved in the OS level. And things start kind of crawling to a halt when you reach a certain point. And you have high number of requests per second, because on any given web page, at most, a single video is playing. Whereas if you search for some search term like dogs, for example, you'll see 60 thumbnails on that one page. So suddenly you have a lot more requests per second. So we started pretty simple, like we generally do everything. We want to get something working. So we started with Apache. We started with a unified pool, meaning the same machines that were serving our web traffic were also serving our static images, or our thumbnails, rather. And we moved to a separate pool, still using Apache. And things were good, and again, until this one email got sent at 2:24 a.m. And if you can't read it, it says, we can't accept any more videos, too many videos. And we found out that the number of files, it turns out that after doing a little bit of digging and frantic Googling and searching for things, we found out that there's actually a per directory limit on the number of files that you can have in that directory. And we had the luxury of time. We could have researched all this stuff ahead of time, but frankly, we were just busy trying to stay alive most of the time. So we ran into this problem, and all the video stopped uploading, and then we had to do a lot of emergency work and stuff like that. And turns out that ext3 in particular had this issue. We since moved to Riser, and we since moved to a more hierarchical directory structure, so we don't have this problem, because it's definitely not a good idea having too many files in one directory anyway. So again, a little bit of the history with thumbnails. We started with Apache. Yeah, unfortunately, it resulted in high load and low performance. Not a good combination. We moved to Squid. We basically put Squid in front of our Apache machines, and it served as a reverse caching proxy. And it was much more efficient with CPU. It did a lot better job at dealing with most requests. It had a nicer threading model and things like that. But we found out that as load increased, performance actually degraded over time to the point where before it might have been serving 300 requests per second, and then afterwards, later on, like a day later or 2 days later, it would only serve maybe 20 requests per second or 10 requests per second. So we actually had a script that would automatically kill it and restart it. So it was kind of the Windows approach of scaling, just restart everything. So we moved to, we tried looking at lighttpd actually, because we were using it for video servers. And the problem is that out of the box, it only has one process. And so every time you need to do a disk read, so every time your content is not in memory already, you need to do a disk read. And that stalls the main event loop. And there's only one loop in the whole system anyway. It stalls that loop this minute amount of time. And the more cache misses you have, the worse it gets. So we tried moving to the multi-process model, where basically a parent would fork off a whole bunch of children, and the children would all be calling accept on the one server socket. But then we'd run into various things like each of the processes would have their separate caches. There was less efficiency. There was a thundering herd problem because there were so many connections happening per second. So there were a lot of issues with having multiple processes just calling accept all the time. So we actually decided to make use of one of lighttpd's big advantages, it being open source. So we modified it. So instead of having everything happen on a single worker process, single process, we had a main thread which handled stuff like the ePoll. It handled stuff like reading memory from reading content from that's already in memory, so that's very fast. And we delegated all of the disk reads into separate worker threads. So the idea being that, well, as long as you keep all the fast stuff on the main thread, you're serving a lot of requests per second, and all the slow stuff can come whenever. It can come half a second later, it can even come a second later in the worst case. Hopefully not though. But since then, we've actually moved on something else, because the reason is that this solution had some fundamental problems that we just didn't address. We were still storing each thumbnail as a separate file on the file system. And even though we'd had a hierarchical structure, directory structure, so that there's some sort of fan out at each level so that you don't have a huge fan out at one particular level, the fact remained that we had so many images that to set up a new machine took about, let's see here, just to tar up the images from one machine to copy to a new machine took 24 to 48 hours. So that's pretty bad. I don't think rsync ever finished, because rsync tried to store everything in memory, and it just exhausted all the memory in the system. The problem is that if you had to reboot a machine, let's say you had to upgrade the kernel or whatever, the machine crashed, it would take about maybe 6 to 10 hours for the machine to warm up for enough images to have been read from disk that you're not stalling on disk all the time. Because you can't spawn an arbitrary number of threads, because after a certain while, you're bottlenecked on disk. So we moved to something that's based on Bigtable, actually. BTFE stands for Big Table Frontend, I think. And this is, as mentioned in Jeff Dean's earlier keynote, a Google technology, a distributed data store. And we store our thumbnails in Bigtable right now. And Bigtable has various forms of chunking, so you don't have all these little files like floating around. So basically, replication and setting up a new machines becomes much better and easier. And it's very fast and fault tolerant. All the Google stuff was built on the premise that the underlying hardware, the underlying network, all of it can be unreliable. So plan for unreliability and just work around it. And it has various forms of caching because with distributed systems, one of the enemies is latency. So especially caused by the distance between the source of the data and the client. So you cache at multiple levels so that the latency between the user and the content is not so much. OK, so the final area that I wanted to talk about was databases, because that's really been the core of a lot of our scalability work. We use MySQL because it was fairly simple. It's very fast if you know how to tune it correctly. And it's used by a lot of websites, so we know its characteristics. It has some flaws, but they're known flaws. They're not flaws that you have to pay somebody hundreds of thousands of dollars to figure out. And so that was an easy choice for us. We store our metadata there. We don't store anything. We don't store our videos. We don't store our thumbnails. We store our metadata, such as usernames, passwords, video descriptions, titles, that kind of thing, messages in our system. So again, we started pretty simple. We started with one main database and one backup. And we were doing fine until, well, people started using our site. I guess somehow the word got out. And load increased. And the problem with most load profiles is that once you load generally increases at a linear rate on a system until you hit a certain point. For a database, it's usually when you start having to go to disk. And then suddenly, the load really, really spikes. So we were having issues with that. And the problem was that we didn't have much flexibility because we were small enough at that time that we were actually leasing most of our hardware. So they could only get new hardware to us so fast. So we later remedied this. But the point remains that during this time, it was a big problem. And one particular day I remember very well because the whole site had crawled to a halt. I was trying to figure out why, tracing things, doing vmstat everywhere, things like that. And it turned out that the main database that we had, the one database that was serving all live traffic, was swapping. So the question is, why is it swapping? I mean, we had configured it so that it's not using more memory than the system has. So the memory is capped at a certain point. So why is it swapping? Why is it bringing down the site? And it turned out that in the Linux 2.4x kernels, at least the earlier ones, I don't know if they fixed this later on, but in the earlier Linux 2.4 kernels, the kernel thinks it knows better than you. It thinks that its page cache is sometimes more important than your application. So what happened was that the page cache was a healthy, 1.6 gigabytes or 1 gigabyte or something like that, and the application was about 3-point-something gigabytes, 3.5 gigabytes or whatever. But the problem is that there was only 4 gigabytes of physical memory. So rather than reducing the size of the page cache, as I would have thought it did, it instead swapped out MySQL. But then the problem is that MySQL really needed to be in memory. So then later on, it decided to change its mind. And then it went back and forth. And basically, we had the swapping in, swapping out. It was horrible. So since kernel upgrade was a few days out of the way, since new hardware was not available at the time, it would have taken at least a day or two. And since the site was really hurting, I basically took a big gamble. I decided that what if, so let's see here. The kernel is swapping out MySQL. So what happens if we took away the swap from the kernel? So that's exactly what I did. I deleted the swap partition while the site was pointing to the database. Yes. And yeah, believe me, that was not a fun morning. I don't think I tasted anything for days, but yeah. And after an hour of even more serious pain because everything was getting swapped in, and there was a lot of disk activity, it turned out that we had about 20 to 30% overhead or headroom on the system. Now we suddenly had 20 to 30% idle CPU. And granted, if our memory usage spiked for whatever reason, the box would have hard crashed. So, but it was sort of a trade-off we had to make for that couple of days until we upgraded the hardware. So, interesting risk that you can take when the whole world isn't really looking at you yet. I mean, that was kind of the nice thing about that back then. So obviously, we had to do a number of database optimizations along the way. We optimized queries. We made real-time operations into batch jobs whenever they were too expensive to do in a real-time basis. We use memcache. So instead of going to the database every single time, we use memcached, which is another open source daemon. It's basically more or less a hash table that listens on a TCP socket and allows you to get and set data using some kind of string-based key. And that was very helpful. That gave us a very nice boost because using memory is a lot better than using disk most of the time. And we use app server caching. So again, we have these various tiers of caching. We can cache. There's the database caches. There's a database machine OS caches. There's memcache, and then there's actually the memory space of the app server process. So in some cases, when we access the data really, really often, like hundreds of times per second maybe, or even dozens of times per second, sometimes it makes sense to pre-calculate the data, replicate it to all the web machines, and just to store that data in memory. And nothing beats local memory access, or at least, I don't know, maybe Google's coming up with something. So another thing that we did was replication. So MySQL has this rather nice facility where, so most websites start with one database, and that works pretty well for a time. As traffic grows, what happens is that you spread read load across other databases, which are basically replaying SQL transactions that are happening on the master database. So the way it works is that all the writes go to one master database, and they get funneled down to every single replica that's attached to that database. This is an asynchronous process, so there's no guarantees about timeliness. So you have to be willing to live with at least a tiny amount of staleness, generally sub-second most of the time. And you have to watch out for the limitations, because all these writes are happening in multiple places. So if the writes grow to a certain point, then you get this situation where the writes are hogging all the replica databases, and maybe 20% of your resources are serving reads. And that's kind of a problem. And another problem with replication that can occur is that if you have too many replicas, you have sort of management issues. You have the fact that you have a single point of failure, that if you have to cut over to a new master database, you suddenly have to reconfigure all these machines. You have a number of issues, and it becomes a kind of a brittle system. Because usually having too many replicas is a symptom of a larger issue. It means that you're not spreading the load evenly enough across multiple machines. So here's a nice quote that you guys can read. I hijacked it. I changed a few words here and there. But so it's kind of true, though. You start off small, it works, but then you expand and things get out of hand. So the other issue is replication lag, or replica lag. And actually, this is actually one of the main downsides of MySQL replication, because MySQL replication doesn't have something like 2PC. It doesn't have any kind of consistent write mechanism. So replication is completely asynchronous. If you have 3 replica machines, and each of them have a different CPU speed, and each of them have different speed disks, you're gonna get slightly different amounts of lag on each of those machines, which is a problem. And here's one of the reasons why it could be a problem, because on the master database, updates actually come in through multiple threads. In this case, there are 3 threads, and each of the threads is executing a single update. And what's nice is that if you have a multi-CPU, multi-core machine, multiple disks, you can exploit the parallelism that your hardware offers you and the OS offers you. However, on the replica database, in their, I guess, infinite wisdom, MySQL serialized everything onto a single thread. So I guess they did it for correctness reasons and for ease of testing and stuff like that. But the point remains that replication on the replicas it can be bottlenecked, because if you have a single long update, let's say the one highlighted in red up there, update 3 cannot execute until update 2 is finished. So you have one thing hogging all the resources, then you're stuck. Because the OS is not, and the OS and the hardware is not generally very intelligent with trying to parallelize a single thread. So here's another kind of variant of that same problem. we have a replication thread, and what happens is that it's doing 5 updates. 3 of the updates affect database pages that are not in memory, so they result in cache misses. Cache misses stall the replication thread, and that can be a problem because after a while, we did as much tweaking as we could in the application, but it came to the point where the replica just could not keep up with the master database because the master database was using all of the CPUs and all of its disks, and the replica can only use 1 CPU and 1 disk, generally speaking. So we thought about it, and we realized that replication, or each update statement in a replication thread, involves 2 steps. It involves reading the affected database pages, and then it involves applying the changes. So obviously I'm glossing over a lot of detail, but those are the high-level steps. So the idea is that because MySQL has actually 1 thread buffering all the SQL on the master database, from the master database, and another one executing the SQL. So in the case where the replica is lagged behind the master, we've actually written the SQL statements that are going to be executed 1 second from now, 5 seconds from now, 10 seconds from now to disk already. So it's just that the replication thread hasn't had the chance to replay them because it's blocking or whatever. So the idea is that what if we prefetch the pages required to perform these updates? So we came up with a little tool. We hacked together a little tool in, I guess, the course of a day or 2, I think. And we came up with the idea that we had a cache priming tool, and that tool would read ahead the SQL buffer. I mean, keep in mind this only works, obviously, if the replication thread is lagging. And it will actually fetch the rows a couple of seconds before the replication thread needs them, therefore ensuring that replication thread just hums along and it just executes every statement very quickly because everything is coming from memory. So this was huge because, again, this reduced our replica lag from a huge amount to a very, very small amount. And it bought us more time because we were working on the longer-term solution, but again, that was longer term. That took a while to implement. So we needed to stay alive during that time. So even with all this trickery, though, the replicas were still falling down. There were too many replicas. It was a management nightmare. We had to add hundreds of thousands of dollars of hardware just to add a little bit of incremental capacity because the writes were so dominant. And there was replication lag. Users were complaining, weird, unreproducible bugs because since replication lag is inherently unpredictable, it was hard to even reproduce some of the bugs. So we had to take some extraordinary measures to stay alive. And unfortunately, some of our team members, I guess, weren't up to the task. So yeah. So we actually took drastic measures, though. We introduced Replica Pools. So rather than having a whole set of replica databases attached to our 1 master database, we actually thought, wait a minute. So we are starting with the assumption that we cannot serve all traffic on the website equally well because our hardware is a few weeks out, our software is a few weeks out. We need to stay alive. So we were thinking, what part of our site matters most to users? And that would obviously be playing videos. And there's a lot of other social networking functionality, but playing videos really is the crux of the YouTube site. So we split the replicas into 2 pools. The watch pool, which basically serve video watching, and consists of very nice queries from a database point of view, like single row lookups. It only hits a certain subset of the tables. So we can exploit the cache locality by kind of confining the queries required to watch videos to a single set of machines, and then everything else gets put into another set of machines because those features involve a lot more database load. They involve more complicated queries. So it's just a lot more work for the databases. And so rather than making everyone suffer, including people who are watching videos, we decided to contain the damage in the general pool and serve the people who are watching videos better. Again, just a stopgap measure, but it's one of the sort of more desperate things that you need to try if things are falling down and everyone's complaining and things are not going so well. So we also looked at our hardware, and we've all looked at our hardware a number of times. This is just one instance of that. And our databases, we're actually serving all of their data off of like a monolithic RAID 10 volume that was local to each machine. So that RAID 10 volume consists of 10 disks, And we noticed that we were spending a lot of time I/O wait as measured by VMstat. And we were just waiting on disk like so much. And then we were hypothesizing that Linux was only seeing one volume, and therefore it wasn't being aggressive with parallelizing disk writes. It wasn't being very aggressive with issuing the writes and the read requests. So we played around with the RAID configuration a bit, and we came up with something that actually turned out to be much better. It was basically exposing each of the constituent RAID 1 mirrors, so 2 disk RAID 1 mirrors, to the operating system, and then relying on Linux's built-in RAID 0 software to stripe them together. So it's basically a hybrid hardware-software RAID 10 configuration. And we did some tests, and they look good, and then we released it live, and it turned out that this helped us a good maybe 20% or so, 20 to 30%, in terms of the throughput and the number of reads and writes that the same set of hard disks can service as measured by IOstat. So this was a huge improvement, obviously. Same hardware, no additional cost, just have to reconfigure a bunch of machines. So that bought us a little bit more time. But again, all this stuff was just not, it was just, some of it was good engineering, some of it was just hacks, and we really needed to get to a solution that would scale us to 4x the size or 8x the size. So that's why I'm going to spare you guys the detailed diagram of what we were doing at the time, because it was just very, very ugly, and it just got untenable. And I'll tell you guys about what happened soon after all these hacks got put into place, because at the same time as some of us were keeping the site alive, some of the rest of us, and keep in mind by some of the rest of us, I basically mean the same people, but nighttime instead of daytime or something like that. Some of the rest of us were actually putting together the long-term solution, so which would generally be partitioning. A lot of problems in computer science can be solved through judicious use of partitioning. So you had this monolithic database, right? And it was gigantic, and it couldn't fit in memory. It was multiple times the size of memory. And got rid of that, and basically split it into multiple shards. So instead of having one user, one database with all the users and all the videos on it, split it up into multiple pieces, and each shard is completely independent of each other. There's no overlap between the shards. And the great thing about this is that you can spread reads and writes, which is a great thing, because that was one of the key limitations of MySQL replication. You improve your cache locality, which is critical because memory is obviously much faster than disk. So the closer your working set is, the closer the size of your working set is to the size of your memory, the better. Otherwise, you spill over to disk, and things get very slow. So, and it turns out that when we released this change, which was a pretty big change, and actually went fairly well, considering the extent of the changes, we were able to serve the same amount of traffic, but with 30% less hardware. And we reduced replica lag from a fairly high number to 0, and where it remains today. So very good, and we can create new shards with some amount of work in the future. So we have sort of a way of scaling our database kind of arbitrarily. It's not trivial, but it's a lot better than it used to be. And obviously, we have less reliance on clever tricks, because as fun as it is thinking about clever tricks, you don't want to have to come up with 5 of them a day to keep the site alive. So okay, to recap, we keep things simple, which is good because you are able to move around simple code more easily. You're able to re-architect it. You're able to split it up into different functions, to rewrite it, to change the algorithm, to do whatever. We constantly iterated on bottlenecks, because whenever you resolve one bottleneck, there's another bottleneck, unless you are willing to spend ridiculous amounts of money on hardware and you have an unlimited budget. So the bottlenecks are obviously software, OS, and hardware. And there's one last thing that actually we do for scalability, or one more important ingredient for the recipe of scalability, which is the team. I mean, it's been a pretty awesome team to work with. I think for the first, I don't know, like 6 months or so, 12 months, I think we were pretty much it in terms of everyone who was keeping the site alive. One person would be handling data center stuff and setting up machines and setting up the printers for the office and just random stuff. So it's pretty cool to have cross-discipline people who understand the whole system. They understand more than just software. They understand the system underneath the software. So that's a pretty critical component. And obviously, it's nice to have cool people to drink with. OK, so future directions. Basically, more of everything. We've had pretty rapid growth. Every time we relieve a bottleneck that's seriously hurting the site, it seems like we grow 20 to 30% kind of overnight, which is a little bit nerve-wracking. Sometimes we think, well, maybe if I just leave it for one more day, I can get some sleep, and I don't have to deal with yet another bottleneck. So there's that. More videos, more formats. We're branching out into a whole bunch of different areas. Like I think there was the Apple ITV thing that was announced recently, and a number of other non-web experiences. More users. Our users keep coming, and we recently localized. So now suddenly the user in Japan, for example, can read our web pages for the first time. We have more data-intensive features. I mean, now we've basically scratched the surface of what you can do with video. Right? We have obviously Google Search, which is obviously a great search engine. We have collaborative filtering, helping to figure out sort of the co-visitation habits of people and recommend more videos based on the current one you're watching. But there's a lot of work that can remain, though. There's a lot of work that remains to be done. There's personalized recommendations. Well, based on the 20 videos I've watched, what other videos am I likely to want to watch after that? There's more group things that we can do. There's all sorts of taxonomies that we can create. There's a lot of categorization, data mining, and stuff like that. And that's actually a weak point of a traditional SQL database, especially MySQL, which doesn't do parallel queries at all. So we're definitely going to play around with a lot of the Google technologies, where stuff like MapReduce and a number of other things that are highly parallel and can spread computation across many, many machines. Because if you're serving hundreds of millions of video views per day, you're not going to be able to mine that data unless you go distributed. So I think that wraps up my presentation, actually. I wanted to keep it reasonably short because obviously it's been a long day. So I'll just leave some time for some questions.
That meant you could move away from doing some of the replication. Do you find now that you're doing replication with shards or not?
We are doing replications, but we're not going nearly as wide, which is a great thing. Because after a while, your replica lag just becomes unmaintainable. It just becomes large, and you can't do anything to reduce it past a certain point. So yeah.
Talk a little bit more about how you partition the user database.
Wow. Well, OK. So basically, we started with a monolithic database, right? And one of the things that we did was we started. I mean, this is a high level. I mean, there's a lot more detail I'm leaving out. But basically, we started instrumenting all of our code. We changed our code and left the database functionality exactly the same. We changed the code so that we could tag each query with the associated user. So the idea being that, OK, how are we going to know what goes where unless we know which user a query corresponds to, especially since a user can have multiple videos, which can have multiple comments, et cetera. So there's a hierarchy of tables here. So you need to go as far down as you go. You need to know exactly which user this corresponds to. That way you know which shard to direct it to. So that was the first step. We released that code. Pretty much no one noticed because that was an invisible change. Then we basically used that information, and we started with snapshots of the database in multiple places for each of the shards. These became the new master databases for the shards, and we basically took a Python script and we used it to divide up the traffic according to the user. So we came up with a partitioning scheme. And we decided that, OK, this shard will replay 1/nth of the stuff, and for this fixed set of users based on our hashing algorithm. And this shard does another disjoint set of users, and so on and so forth. We kept on kind of replaying stuff. We verified for a fairly long period of time. We made sure that all the data was there, stuff like that. We tested on a small set of users. And then afterwards, we basically did the cutover. We took pretty much a hard downtime or close to a hard downtime. And we switched the writes to the new shards because they were replaying all the sequels and they were perfectly in sync with the master database, especially after all the site traffic had stopped to the master database. And then we pointed the application to the new databases. So that's it at a high level. I mean, there's a couple other things. Like in order to associate users, in order to map users to shards, we have a lookup database that's heavily cached. We have a database that maps user IDs to shards. And the reason being that, yes, we can use a mathematical algorithm. But the problem is that we found out through talking to a couple people in different companies that the shards tend to get lopsided because one user happens to be a particular power user, or this group of users tends to be a power user, set of power users. And that shard becomes unbalanced. So you have to at some point be able to move users between shards arbitrarily. Back there?
Can you talk about bandwidth and hosting?
Huh?
Was bandwidth inbound or outbound an issue, and how do you host the service?
Okay, so inbound bandwidth. Okay, so the question is, like, how did we deal with bandwidth? Was inbound or outbound bandwidth an issue? How did we host the service? So inbound traffic, not at all an issue. I think we would make a great BitTorrent peer because we were actually considering that for a while, but merely from Linux ISOs, mind you. But anyway, so inbound traffic is not an issue. Outbound is certainly had to scale quite a bit, and basically our networking team of 2, which grew by a whopping 50% after the acquisition, had to fly all these different places, pre-wire stuff, had to negotiate all these peering agreements, and et cetera. And basically, that was sometimes an issue because of the speed at which the site was growing. It's like, oh, let's add another 10 gigabits here or 10 gigabits there. It becomes kind of challenging to keep up with that, especially with a small team. And furthermore, some of the bigger guys, some of the telcos didn't want to peer with us for a while because, for whatever reasons. And I guess those were the main issues. I think our costs actually were exceptionally low for the most part. We were able to negotiate fairly competitive rates. I can't mention specific numbers for various reasons, but I can say that as our traffic grew, our cost per megabit per second went down drastically. So, and we also use CDNs to help with that because CDNs replicate the content in multiple places. So the chances of the content living closer to the user and therefore going through fewer hops and friendlier networks tends to be higher. So in terms of hosting, we started early on with managed hosting because, again, when you're living off your credit cards, personal credit cards, you can only do so much, right? We didn't have a sysadmin at first. We didn't have anything. Like we just had a couple of developers and maybe one business person. And we went through several managed hosting providers, but it became clear that all these guys just couldn't scale with us. I mean, and furthermore, we would get these weird complaints. Like, for example, we get a DMCA complaint, which basically is an official complaint by copyright holders saying, you need to take down this video. And of course, we'll comply. The problem was the handling of this for the managed hosting providers. We got this one phone call from the hosting provider saying that there's just one reported DMCA violation. Fix it in 1 hour, otherwise we're shutting down your site. So not a very good situation. And obviously you can't control your hardware, you can't control your networking agreements, you can't control anything. So we set up our own colo presences in various Equinix centers, and it turned out to be a wonderful decision. Greater flexibility in software and hardware. We can negotiate all of our networking stuff. We can basically customize everything to our heart's content. Yeah, right here.
Did your infrastructure enable supporting H.264 pretty easy, smooth, trivial?
It's actually we're actually using Google infrastructure for that mainly because we wanted to make sure that our the question was, does the YouTube infrastructure take care of serving H.264 and handling H.264 easy? And basically, we use Google infrastructure for that mainly because we wanted our servers to have a pretty homogeneous profile. We wanted to make sure that they have similar bit rates for all the videos and stuff like that. That way all the tuning that we've done to the caches and the disks and stuff like that still held true. Like still were fairly optimal. So we shoved that over because the converting videos and especially mass converting older videos into H.264 is obviously a very distributed problem. And that's where the Google infrastructure shines. Yeah, back there. The question is, do we have multiple data centers? And we do. We have a number of them around the U.S. We have colo presences in each of them. And I think the number is at 5 or 6 right now, I believe.
So follow-up, how did you deal with users in the different data centers? Log in and things like that.
Well, we concentrated most of our things in like a couple of data centers, so that way we don't have to deal with cross data center latency and stuff like that. Obviously, that's a bit of a reliability concern, and we're working to address that. In terms of the videos actually come from like random data centers, or when I mean random, I mean they're not assigned according to closeness to user. That we don't do like CDN-like replication because that's what the CDN is for. I mean, if a video needs that kind of replication, then it's probably popular enough to be seeded into the CDN. So with videos, one of the nice things about videos is that they are not particularly latency intensive, they're more bandwidth intensive. The fatness of your pipe matters more than how fast each packet goes back and forth. So even though, let's say this video is coming from Virginia and I'm in California, it's not that big of an issue as long as obviously there aren't like huge bottlenecks in the middle somewhere. For images, it becomes more of an issue because there's a lot of little round trips, and there could be like 60 round trips on a given page, and that's one of the advantages of the Google BTFE stuff, because that stuff is replicated across different data centers, and Google has a really good way of figuring out which is the closest data center for the user based on a number of different metrics.
All right, why don't we take a minute to thank Cuong for coming out and talking.